First, duality. Let f be a function of two variables. Hold x fixed, and what remains is a function of y alone. So each x yields a function, and that correspondence is itself a mapping from A into the set of all functions from B to C. The converse holds too. Given a mapping from A into that set of functions, we can fill the values back in to get a function of two variables. So the two-variable function and the two mappings are three ways of viewing one phenomenon. The outer two are said to be dual. The first application is the matrix. An m by n matrix is a function defined on pairs of a row index and a column index. Fix the row index, and you get a whole row. So the matrix can be read as a tuple of rows. Dually, it can be read as a tuple of columns. In the same vein, an n-tuple of functions from A to B can be regarded as a single function whose values are n-tuples in B. A more important case comes later. Duality is what lets a finite-dimensional vector space be regarded as its own second conjugate space. Geometry has it too. Take points and lines as two kinds of primitive object, with an incidence function that is 1 when the point lies on the line. Fix a line, and you get the set of points on it. Fix a point, the lines through it. This duality is basic to projective geometry. When a variable is held fixed, there is a convenient device. Put a dot in the position of the varying one. The notation is useful but flawed, since we cannot indicate substitution without losing meaning. From the value, we cannot read back which function was evaluated. Now the Boolean operations. Fix a domain and take a family of its subsets. The union of the family is the set of elements belonging to at least one of them, and the intersection is the set of those lying in every one. Indexing the family makes all of this easier to write. The complement of a subset is what is left of the domain. De Morgan's law says the complement of an intersection is the union of the complements, and this is an immediate consequence of the rule for negating quantifiers. Not always and means the same as sometimes not in. There are also identities for preimages. A preimage preserves unions, intersections, and complements. Only the first survives when the function is replaced by a general relation. The other two fail, because swapping the order of two quantifiers changes the meaning. Finally, partitions. Cut a set into a disjoint family of subsets whose union is the whole set. That is a fibering, and each piece is a fiber. Sending a point to its own fiber is the projection. Any function automatically fibers its domain into the sets where it is constant. An equivalence relation is reflexive, symmetric, and transitive. Every fibering gives one, and the theorem of this section is the converse. Every equivalence relation is the equivalence relation of a fibering. The rationals and the integers modulo p are both built this way.